All right, what is up, you guys? Welcome back to my channel, Anthony Makes Videos. I'm Anthony, and we're gonna get right into the reading today. We are reading section 31, Basic Rules of Tensor Calculus, which starts on page 99 from the book Differential Geometry by Erwin Kreisig. That's in chapter 3. There's a link down below if you want to get it on Amazon. Otherwise, let's get into it. Two tensors are said to be of the same type if they have the same number of contravariant indices and the same number of covariant ones. By addition of corresponding components of two tensors of the same type, A sub alpha 1 through alpha r and superscript beta 1 through beta s, and B sub alpha 1 through alpha r and superscript beta 1 through beta s, we obtain a tensor with components S subscript alpha 1 through alpha r and superscript beta 1 through beta s, which is equal to A with the subscript alpha 1 through alpha r and superscript beta 1 through beta s, plus B with the subscript alpha 1 through alpha r and a superscript beta 1 through beta s. Also, this is using the summation notation convention, which was introduced in section 27. This tensor that we just obtained is called the sum of those tensors. If we multiply every component of a tensor by a scalar, we obtain a tensor of the same type. In consequence of this multiplication and of the above addition, the totality of tensors of the same type form a vector space. Any tensor of second order can be represented as a sum of a symmetric tensor and a skew-symmetric one. We have A sub alpha beta equals 1/2 times the quantity A sub alpha beta plus A sub beta alpha, closed quantity, plus 1/2 quantity A sub alpha beta minus A sub beta alpha, closed quantity, and the tensor in the first brackets is symmetric while the tensor in the second ones is skew-symmetric. Also, just a recap, a symmetric matrix is one such that it is equal to its transpose, and a skew-symmetric matrix is one such that the matrix is equal to the negative of its transpose. So that's going to come into play in the problem that's in a little bit. If we multiply every component of a tensor A sub alpha 1 through alpha r superscript beta 1 through beta s by every component of another arbitrary tensor, B subscript gamma 1 through gamma r and superscript kappa 1 through kappa s, we obtain a system of products H with a subscript alpha 1 through alpha r as well as gamma 1 through gamma r, and then a superscript of beta 1 through s as well as kappa 1 through kappa s in the superscript, which is then equal to A with the subscript alpha 1 through alpha r and a superscript beta 1 through beta s times B with the subscript gamma 1 through gamma r and a superscript kappa 1 through kappa s. Again, this is all with the summation notation introduced previously in section 27, and this product is called the product or outer product of these tensors. As can be seen from the transformations for a mixed tensor, the product of any two tensors is a tensor. The order of this tensor is the sum of the orders of the two given tensors. The number of covariant or contravariant indices of the product is equal to the sum of the numbers of covariant or contravariant indices of the given tensors. Example 1. By means of the transformation law of the tensors A sub alpha beta and B sub gamma superscript tau epsilon, we find that the product A sub alpha beta times B sub gamma superscript tau epsilon has the transformation law A over bar sub kappa lambda times B over bar sub mu superscript nu sigma equals A sub alpha beta times B sub gamma superscript tau epsilon times partial U alpha partial U over bar kappa times partial U beta partial U over bar lambda times partial U gamma partial U over bar mu times partial U over bar nu partial U tau times partial U over bar sigma partial U epsilon. That is, this product is a tensor of fifth order, covariant of third order, and contravariant of second order. Another example of a product of tensors is the product of vectors, which was considered in the preceding section. If we equate two indices of a mixed tensor, a contravariant index and a covariant one, and sum with respect to this pair of indices, we obtain a tensor of order 1 less contravariant and 1 less covariant, as follows from the transformation law for a mixed tensor. This process is called contraction of the given tensor. Example 2. By contraction of a mixed tensor of second order, for instance, a sub alpha superscript beta, we obtain a scalar. A sub alpha superscript alpha equals a sub 1 superscript 1 plus a sub 2 superscript 2 plus etc. through a sub n superscript n, since in consequence of the transformation law for a contravariant vector, and that one I didn't write down either. Man, today is rough. The relations partial u alpha partial u over bar gamma times partial u over bar gamma partial u beta equals Kronecker symbol or delta with a subscript beta and a superscript alpha, where alpha and beta each can be respectively 1 through n. And similarly, partial u over bar alpha partial u gamma times partial u gamma partial u over bar beta equals the Kronecker symbol again with a subscript beta and a superscript alpha, and alpha and beta correspondingly being 1 through n. And the Kronecker symbol, of course, equals 0 when alpha does not equal beta, and it equals 1 when alpha does equal beta. In consequence of these, we thus have a over bar sub gamma with a superscript gamma equals a sub alpha superscript beta times partial u alpha partial u over bar gamma times partial u over bar gamma partial u beta, which equals a subscript alpha superscript beta times Kronecker symbol or delta with a subscript alpha and a superscript beta, which then equals a sub alpha superscript alpha. Example 3. By contraction of the tensor a sub alpha beta superscript gamma kappa epsilon with respect to beta and gamma, we obtain the tensor a sub alpha beta superscript beta kappa epsilon, which is of third order, covariant of first order, and contravariant of second order. Indeed, in consequence of the transformation law for mixed tensors, we have that a over bar sub mu nu superscript nu sigma tau equals a sub alpha beta superscript gamma kappa epsilon times partial u alpha partial u over bar mu times partial u beta partial u over bar nu times partial u over bar nu partial u gamma times partial u over bar sigma partial u kappa times partial u over bar tau partial u epsilon, which is equal to a sub alpha beta superscript gamma kappa epsilon times partial u alpha partial u over bar mu times partial u over bar sigma partial u kappa times partial u over bar tau partial u epsilon times Kronecker symbol subscript gamma superscript beta. Therefore, a over bar sub mu nu superscript nu sigma tau is equal to a sub alpha beta superscript beta kappa epsilon times partial u alpha partial u over bar mu times partial u over bar sigma partial u kappa times partial u over bar tau partial u epsilon. When contraction is applied to the product of two tensors with respect to indices of different factors of the product, the resulting tensor is called an inner product of those tensors. Example 4. The inner product of the vectors a superscript alpha and b subscript beta is the scalar a superscript alpha b subscript alpha. Contraction may be applied in more than one way. From the tensors a sub alpha beta and b superscript gamma kappa epsilon, we can obtain different inner products. A sub alpha beta times b superscript beta kappa epsilon. Contraction may also be applied more than once. When we apply contraction twice to the above product, tensor a sub alpha beta times b superscript gamma kappa epsilon, we obtain covariant vectors such as a sub alpha beta times b superscript alpha beta epsilon, or a sub alpha beta times b superscript gamma alpha beta, etc. Further examples will be included in the following sections. Problem 31.1. Prove if a superscript alpha beta is a symmetric tensor and b sub gamma kappa is a skew-symmetric one, a superscript alpha beta times b sub alpha beta equals 0. Okay, so a superscript alpha beta times b subscript alpha beta equals, now expanded out, a superscript 11 times b sub 11 plus a superscript 12 times b sub 12 plus a superscript 21 times b sub 21 plus a superscript 22 times b sub 22. Now, since a superscript alpha beta is skew-symmetric, then a superscript 11 equals a superscript 22, which equals 0, and a superscript 21 equals negative a superscript 12. Then, since b sub alpha beta is symmetric, b sub 12 equals b sub 21. Therefore, when all these things combine, A superscript alpha beta times B sub alpha beta equals 0. Problem 31.2. Verify that if two coordinate transformations u over bar beta equal to the function u over bar beta with entries u1, u2, etc. through un, where beta can be 1 through n, and u double over bar gamma, which is equal to the function u double over bar gamma in terms of u over bar 1, u over bar 2, etc. through u over bar n, where gamma can be 1 through n. Verify that if these two coordinate transformations are carried out successively, then the components of a tensor with respect to the coordinates u double over bar gamma are related to those with respect to the coordinates u alpha by formulae of the type as the transformation law for mixed tensors. Let us denote by d double over bar the tensor with respect to the coordinates u double over bar gamma occurring in the transformation law for mixed tensors. If we insert into this transformation law the relation analogous to the exact form given in the book, then we have d double over bar subscript kappa 1 through kappa r and superscript lambda 1 through lambda s equals d over bar subscript gamma 1 through gamma r and superscript eta 1 through eta s times partial u over bar gamma 1 partial u double over bar kappa 1 times etc. through partial u over bar gamma r partial u double over bar kappa r times partial u double over bar lambda 1 partial u over bar eta 1 times etc. through partial u double over bar lambda s partial u over bar eta s. Then, in consequence of the following relations for these given partial derivatives, partial u over bar gamma sub rho partial u double over bar kappa sub rho times partial u alpha sub rho partial u over bar gamma sub rho equals partial u alpha sub rho partial u double over bar kappa sub rho. Similarly, partial u double over bar lambda sub sigma partial u over bar eta sub sigma times partial u over bar eta sub sigma partial u beta sub sigma is equal to partial u double over bar lambda sub sigma partial u beta sub sigma, where rho can be 1 through r and sigma can be 1 through s. And we immediately obtain the statement in the problem that we're looking for. Section 32, vectors in a surface, the contravariant metric tensor. In the preceding 3 sections, we have introduced the important concepts of contravariant and covariant transformation. We have also investigated the basic facts of tensor calculus. We will now apply the knowledge gained to problems of the theory of surfaces. We therefore restrict the dimension of the Riemannian space again to the particular value n equals 2. That is, we consider only surfaces. Hence, any summation to be carried out in consequence of the summation convention is to be understood as summation from 1 to 2. Only in spaces in which no metric tensor has been introduced are contravariant and covariant vectors entirely different and independent things. In Riemannian spaces, however, we may correlate these two types of vectors and, moreover, interpret them geometrically in a simple manner. We consider a surface S embedded in Euclidean space R3. We assume that x1, x2, and x3 are Cartesian coordinates in R3, and u1 and u2 are allowable coordinates on the surface S. A vector v bound at a regular point P of S, which lies in the tangent plane E of P to S at P, is called a vector in the surface S at P. The vectors in S at P are therefore a subset of the set of all vectors bound at the point P. Of course, any such vector v is uniquely determined by its 3 components P1, P2, and P3, lowercase, with respect to the Cartesian coordinate system in space R3 and by the coordinates of P. However, it is natural to determine v with respect to a simple coordinate system in the tangent plane E of P. E of P is spanned by the vectors x1, which is equivalent to the partial derivative in terms of u1 of the vector x, that is partial x, partial u1, and x2, which is equivalent to the partial derivative of x with respect to u2, that is partial x, partial u2. See previous section 26. These two vectors are tangent to the coordinate curves through P, the point on the surface S. The lengths of these vectors are the square root of the quantity, the dot product of x1 with itself, which is equal to the square root of g sub 1, 1, where this is the fundamental form, which is again from a previous section, and the square root of the quantity x2 dot product with itself, which is equal to the square root of g sub 2, 2, respectively. We now introduce capital E of capital P, a system of parallel coordinates with origin at capital P, so that the terminal points of the vectors x1 and x2 are the unit points on the axes of this system. By definition, any vector v in the surface capital S at P lies in the tangent plane capital E of P and is therefore a linear combination of the vectors x1 and x2, that is of the form v equals a superscript alpha times x sub alpha, which is equal to a superscript 1 times x1 plus a superscript 2 times x2, where the cross product of x1 and x2 is non-zero. If the coordinates u1 and u2 on capital S, the surface, are kept fixed, v is uniquely determined by the coordinates of the point capital P and the two numbers a1 and a2. To every ordered pair a1, a2, there corresponds a vector in capital S at capital P and vice versa. This correspondence is 1 to 1. The numbers a1 and a2 are the lengths taken with a suitable sign of the respective parallel projections of v upon the x1 and x2 axis of the coordinate system in capital E of P, measured in units of the square root of g sub 1, 1 and square root of g sub 2, 2, respectively. In other words, a1 and a2 are the components of v with respect to the coordinate system in the tangent plane capital E of P. See figure 38 below. Let now u alpha, which is equal to the function u alpha of u over bar 1, u over bar 2, where alpha can be 1 or 2, let u alpha be an allowable coordinate transformation, and let u over bar beta, which is equal to the function u over bar beta of u1 and u2, be its inverse. The vector v can be represented with respect to the new coordinates u over bar 1, u over bar 2 in a manner analogous to the relation v equals a superscript alpha times x sub alpha. Vector v is equal to a over bar superscript beta times the vector x with a subscript beta over bar, where x with the subscript beta over bar is equivalent to the partial derivative of x in terms of u over bar beta. So we have partial x partial u over bar beta. Now, since x with a subscript alpha is equal to x with a subscript beta over bar times partial u over bar beta partial u alpha, then we find that the vector v is equal to a superscript alpha times vector x with a subscript alpha, which is equal to a superscript alpha times x subscript beta times partial u over bar beta partial u alpha. And comparing this with that earlier relation, vector v equals a superscript alpha times vector x subscript alpha, but with a over bar and beta over bar, then we obtain that a over bar superscript beta is equal to a superscript alpha times partial u over bar beta partial u alpha, where beta can be 1 or 2. These relations are of the form of the contravariant transformation law given in a previous section. So that is, if the coordinates on capital S are transformed, the quantities a1 and a2 undergo a contravariant transformation. Thus, a1 and a2 are called the contravariant components of the vector v. And so now we're going to sum up the results thus obtained. Theorem 32.1. The contravariant components a superscript alpha of a vector v in a surface capital S at a regular point capital P are the lengths, taken with a suitable sign, of the parallel projections of the vector v on the axes of a parallel coordinate system in the tangent plane capital E of capital P to the surface capital S at the point of interest capital P with origin at capital P and with the terminal points of the vectors x1 and x2 as unit points on the axes. Those lengths are measured in units of square root of g sub 1, 1 and the square root of g sub 2, 2 respectively. Instead of taking the parallel projections of the vector v on the axis of the above coordinate system, we can just as well take its orthogonal projections on these axes. Let gamma sub alpha be the angle between the vector v and the x sub alpha axes, where alpha is equal to 1 or 2. Then the length of the orthogonal projection of the vector v upon the x sub alpha axis is given by the expression capital L sub alpha is equal to the magnitude of v times the cosine of gamma sub alpha equals the magnitude of x sub alpha over the magnitude of x sub alpha times the magnitude of v times cosine of gamma sub alpha, which is equal to a fraction with the numerator of the dot product between x sub alpha and v. So we have in the numerator x sub alpha dot v over in the denominator we have the square root of the quantity, the dot product of x alpha with itself. So we have the square root of the quantity x alpha dot x alpha in the denominator of this fraction. This is equal to another fraction whose numerator is equal to the dot product of x sub alpha and v. So in the numerator we have x sub alpha dot v over the square root of g sub alpha alpha, where alpha is equal to 1 or 2. Also, this is not a sum, so we're not going to be summing with respect to alpha. This is not part of that whole summation notation from earlier. Hence, the number a sub alpha is equal to the dot product of x sub alpha and v, where alpha can be 1 or 2. And this number is the length, taken with a suitable sign and measured in units, of 1 over the square root of g sub alpha alpha of the orthogonal projection of the vector v on the x sub alpha coordinate axes in the tangent plane capital E of capital P, where alpha can of course be 1 or 2. And this is shown in figure 39 on the previous page, but I'll make sure it's on the screen now if it isn't already. Of course, these numbers depend on the choice of the coordinates on capital S. If we introduce new coordinates, u over bar 1 and u over bar 2, then a over bar sub beta is equal to x subscript beta over bar dot product with v, which is equal to x sub alpha times partial u over bar beta dot product with v, which is then equal to a sub alpha times partial u over bar beta, where beta can be 1 or 2. These relations are of the form of a covariant transformation law, so the quantities a1 and a2 are therefore called the covariant components of the vector v. The correspondence between the ordered pairs a1, a2 and the vectors in the surface capital S at the point capital P is 1 to 1. We have thus obtained the following results. Theorem 32.2. The covariant components a sub alpha of a vector v in a surface capital S at a regular point capital P are the lengths, taken with a suitable sign and measured in units, of 1 over the square root of g sub alpha alpha of the orthogonal projections of the vector v upon the axes of the coordinate systems appearing in the previous theorem. The covariant components of a vector v in capital S at capital P can be obtained from its covariant ones and vice versa by inserting vector v equals a superscript alpha times vector x sub alpha into a sub alpha equals vector x sub alpha dot product with v. We have that a sub alpha equals x sub alpha dot product with v, which is equal to x sub alpha dot product with a superscript beta times x sub beta. Hence, in consequence of the notation where vector x sub alpha dot product with x sub beta is equal to g sub alpha beta, then we have that a sub alpha is equal to g sub alpha beta times a superscript beta, where alpha can be 1 or 2. Since g, which is equal to the determinant of g sub alpha beta, is non-zero, we can solve this system of linear equations for a superscript beta. We obtain a superscript beta equals g superscript alpha beta times a sub alpha, where beta can be 1 or 2, where g superscript 1 equals g subscript 2 over g. Also, g superscript 1 2, which is equal to g superscript 2 1, is equal to negative g subscript 1 2 over g, and g superscript 2 2 is then equal to g subscript 1 1 over g. Taking the inner product of both sides of a superscript beta equals g superscript alpha beta times a sub alpha, and an arbitrary covariant vector b sub beta, we have that b sub beta times a superscript beta is equal to g superscript alpha beta times a sub alpha times b sub beta. The left-hand side of this expression is an invariant, and consequently so is the right-hand side. Hence, the quantities g superscript alpha beta are the components of a contravariant tensor of second order, which is called the contravariant metric tensor. Since g sub alpha beta is symmetric, g superscript alpha beta is also symmetric. Two tensors a sub alpha beta and b superscript gamma kappa with non-vanishing determinant, namely determinant a sub alpha beta is non-zero, and determinant of b superscript gamma kappa is non-zero. These two tensors are said to be conjugate if the relations a sub alpha beta times b superscript beta gamma equals Kronecker delta symbol sub alpha superscript gamma is equal to 0 when alpha does not equal gamma, or equals 1 when alpha does equal gamma. So if that relation holds, that is, if the corresponding matrices a sub alpha beta and b superscript gamma kappa are inverse to each other. The covariant and the contravariant metric tensor are conjugate for g sub alpha gamma times g superscript gamma beta, which is equal to the Kronecker delta subscript alpha superscript beta. In consequence of the quantities g superscript alpha beta, which are the components of a contravariant tensor of second order, which is called the contravariant metric tensor, we obtain that g star is equivalent to the product of g superscript 1, 1 and g superscript 2, 2 minus the square of g superscript 1, 2, which is thus equal to 1 over g. We mention the following fact. The tangent plane is spanned by the covariant basis vectors x sub alpha, see above, or equally well by the contravariant basis vectors x superscript alpha equals g superscript alpha beta times x subscript beta, where alpha can be 1 or 2, in terms of which x sub alpha equals g sub alpha beta times x superscript beta, and the dot product of x subscript alpha and x superscript beta is equal to the Kronecker delta subscript alpha superscript beta. Then corresponding to a sub alpha equals the dot product of the vectors x sub alpha and v, we thus have a superscript alpha equals the dot product of x superscript alpha and v, where alpha equals 1 or 2. If the coordinate system on the surface capital S is Cartesian at the point capital P, that is, if at capital P, g sub alpha beta equals the Kronecker delta with a subscript alpha beta, which is equal to 0 when alpha does not equal beta and 1 when alpha does equal beta, then at this point g equals 1, and therefore g superscript alpha beta equals Kronecker delta with a superscript alpha beta, which similarly equals 0 when alpha does not equal beta and equals 1 when alpha does equal beta. Hence, in this case, a sub alpha equals a superscript alpha, and alpha can be 1 or 2. Indeed, then the square root of g sub alpha alpha equals 1 over the square root of g sub alpha alpha, which is equal to 1, and the orthogonal projections of the above vector v coincide with its parallel projections. Consequently, in Euclidean spaces, when Cartesian coordinates have been introduced, there is no difference between contravariant and covariant components of a vector. As we have seen, the transition from covariant to contravariant components and vice versa can be accomplished by taking the inner product of the components and the metric tensors. More generally, by means of the metric tensors, from a given tensor we can obtain tensors of the same order but of different type. Examples: a superscript alpha beta equals g superscript alpha gamma times a sub gamma superscript beta, and a superscript alpha beta equals g superscript alpha gamma times g superscript beta tau times a subscript gamma tau. We also have a sub alpha superscript beta equals g superscript beta gamma times a subscript alpha gamma. We also have a sub alpha beta equals g sub alpha gamma times a superscript gamma subscript beta, in that order. So the superscript comes first and then the subscript comes second. That's important. Similarly, there's a sub alpha beta equals g sub alpha gamma times g sub beta tau times a superscript gamma tau. This is just funny, but when it's when there's g sub alpha gamma, it looks like it says gay. Sorry, that's immature, but I just had to say that. Okay. A sub kappa and then superscript alpha beta equals g sub kappa gamma times a superscript gamma alpha beta. Also, a sub kappa alpha superscript beta equals g sub kappa gamma times g sub alpha sigma times a superscript gamma sigma beta, and a sub kappa alpha beta equals g sub kappa gamma times g sub alpha sigma times g sub beta tau times a superscript gamma sigma tau. We say that these tensors are associate to the given tensors by means of the metric tensors. We speak of this process as lowering superscripts by means of g sub alpha beta and raising subscripts by means of g superscript alpha beta. This process is reversible. For example, if we take the inner product of a mixed tensor a sub gamma superscript beta and g superscript alpha gamma, g superscript alpha gamma times a subscript gamma superscript beta equals a superscript alpha beta, and then the inner product of a superscript alpha beta and g sub alpha kappa, we obtain the original mixed tensor. G sub alpha kappa equals a superscript alpha beta, which is equal to g sub alpha kappa times g superscript alpha gamma times a subscript gamma superscript beta, which is equal to the Kronecker delta with the subscript kappa and a superscript gamma times a sub gamma superscript beta, which is equal to, finally, a subscript kappa superscript beta. In consequence of this possibility of lowering and raising indices, it is advantageous to write, for instance, a, and then in its own column space, essentially, we have alpha 1 through alpha r, and then in another column space, we have beta 1 through beta s, and not writing a, and then within the same column space, the superscript beta 1 through beta s directly above alpha 1 through alpha r. At the beginning of an investigation, the order of the covariant and contravariant indices of a tensor may be arbitrarily chosen. This order is then fixed in the course of this investigation. All right, so that's 2 sections, got into a little bit of the basics of tensor calculus. I think I'm gonna cut it off right there for now, and hope you guys enjoyed. See you in the next one, and we will keep reading.